Hello and welcome to section 7.4 of our linear algebra notes, the singular value decomposition. And so the first thing we'll do is we'll learn how to maximize the length of a times x over all unit vectors x for just an arbitrary matrix. And then we'll construct the singular value decomposition. And the idea behind all of this is sometimes we have a matrix that's not diagonalizable. And the singular value decomposition allows us to do something that's kind of similar to diagonalization. Okay, so first of all, we want to know what the eigenvalues of a square matrix tell us about the linear transformation. So these values actually tell us how much by what amount our matrix A stretches or shrinks our eigenvectors. And in fact, it turns out that the biggest eigenvalue corresponds to an eigenvector in the direction of the greatest stretch. And that might actually be, so maybe I should say the direction of the greatest scaling, because it might actually be the case that the that the matrix A shrinks everything by a little bit, but so you want the kind of the least amount of shrink. Or the greatest stretching effect, I guess, is another way to think about it. Okay, so let's let A be a given matrix. And what we want, in this case, it's a 3x2 matrix, 3 rows and 2 columns. So we already know it's not diagonalizable, so we can't do our typical process to it because it's not even a square matrix. But we want to find, so our first step in this process is to find a unit vector. And remember, a unit vector means that the length of that vector just equals 1. So if you think about there being a circle or a sphere around the origin, it's a vector that ends inside that sphere. And then we want to maximize the length AX. And then we want to go ahead and compute this maximum length. So let's note something interesting about that length. Then we'll go ahead and square it just to have something slightly easier to work with. So the square of the length, remember the length is the square root of the dot product of a vector with itself. So the square of the length is the dot product of the matrix AX and itself. And so that's equal as matrix multiplication to taking the transpose of the first times itself. And then when we do our transpose, just like the inverse, we can distribute our transpose, but we swap the order. And so we get X transpose A transpose, and then times AX. And finally, that is going to equal X transpose times, and then we have this nice matrix A transpose A times X. Well, I say this is nice because it has lots of nice properties. And so our only quiz today asks you to think about what is not always true of our matrix A. So of our matrix A transpose A. So our matrix now has a lot of different properties, but one of these is not always going to be true. And so this quiz might take you a while to think about. My hint for invertibility is to try something like A, B, C, D. And I guess if that's our A transpose looks like A, B, C, D. And try to see what A, B, and C and D might have to be to make the resulting matrix not invertible. For symmetric, well, to show that something's symmetric, you want its transpose to equal the original matrix. So see if that's true. And that's a little hint to get you going on your quiz. Okay, so we need to maximize, right? So we're trying to find the maximum value of AX. We know now AX length is looking like a quadratic form because we have Q of X equals, and then we have X transpose times our matrix times X, subject to the constraint that the length of our X value has to equal 1. Okay. Well, it turns out, and this is something that we won't go into why this is true, but the maximum value is actually attained at a unit vector corresponding to the largest eigenvalue of A transpose A. Okay, so now we just need to find our eigenvalues of A transpose A, and so we write down A transpose, we multiply it by A. When you do that multiplication out, and as always, you can pause and double check your multiplication and then join back up, we get 17, 8, 8, 17. And if you do your eigenvalue calculations, you'll get two eigenvalues. One is lambda equals 25, and one is lambda equals 9. And we want the largest one, so we are going to focus in on lambda equals 25, and we want to find an eigenvector. So when we subtract 25, we get negative 8, 8 on top, 8, and then 17 minus 25 is also giving us negative 8. We row reduce that to this matrix 1, negative 1, 0, 0, and that corresponds to our basis for that eigenspace. Again, you can pause it and do this out. I'm not going to write out this equation, but you get the vector 1, 1. We want a unit vector in that direction, so we divide by the length, and the length of that vector is the square root of 2. Again, I'm pulling a lot of different things together, so you may have to pause it and remind yourself, how do I compute the length of a vector? And you'll see that you should get root 2. You dot it with itself and then take the square root. Okay, and so then it also asks us to compute this maximum length. So we want the length of A times, let's call this vector V1. So we want the length of A times V1. And so A here is 3, 2, 2, 3, 2, negative 2, and we're multiplying it by 1 over root 2, 1 over root 2, and then we want the length of that. So when we do this multiplication, let's see, we get a 3 by 1 vector, we get 5 over root 2, 5 over root 2, and 2 minus 2, so we get 0 over root 2. And the length of that is going to be the square root of 25 halves plus 25 halves equals 5. So 5 is the maximal length of AX when X is restricted to be a unit vector. And why it's important to restrict to that, by the way, is because that lets us go in every possible direction, but it doesn't allow us to start with really big vectors that are then just going to get even bigger, because then you could just go on forever. You can always make AX bigger and bigger and bigger. So we need some sort of constraint so it doesn't go on forever. Okay, so now we're going to talk about something called the singular values. And these are going to turn out to just be the square root of the eigenvalues. But in order to be able to take a square root, we need to start with a non-negative number. So it could be 0 or something positive. And so why is it that our matrix A transpose times A always has non-negative eigenvalues? Well, we know A transpose times A is symmetric. Hopefully you got that right on your quiz question. And so that means that it can be orthogonally diagonalized and so let's let v1 through vn be an eigenvector basis for Rn. We get through our orthogonal diagonalization process. And we have our corresponding eigenvalues. We're writing them, the eigenvalue that corresponds to each eigenvector. And so repeats are possible here. Okay, so let's now look at the length. And you might wonder why I'm doing this. Why I'm all of a sudden taking the length of AVI squared. And you'll see why in a moment. So bear with me on this. So remember that to take the length squared, we take our vector AVI and transpose it times our vector AVI. And that equals, again, we distribute our transpose and flip the order. And so we get A transpose A in the middle here. But VI is an eigenvector for A transpose A. So what that means is that we can replace this part in pink with the corresponding eigenvalue times VI. Because remember, eigenvector means that AX equals lambda x. So we replaced AX. In this case, it was A transpose AX equals lambda x. But lambda I is a constant, and so we have a theorem in chapter 6. And I'm writing down theorem from chapter 6, but you should go back and cite down which one that says we can pull out. It's a dot product theorem. But now V transpose, let me use a different color, V transpose VI is actually the length of VI squared. But that's a unit vector. And so this just becomes lambda I times 1, which is just lambda I, since VI is a unit vector. Unit vector meaning length 1. But now look at what we have. So we have the square of a number equals our eigenvalue. If our eigenvalue is the square of something, it can't be a negative number. So that's how we know that our eigenvalues all must be non-negative. Okay, so since they're non-negative, we can take their square roots. And so the square roots of the eigenvalues of A transpose A, which in our particular example were 25 and 9, are the singular values. So sigma 1 is the square root of lambda 1. So that's just 5. And sigma 2 is the square root of lambda 2. And so that is 3. And that 5 appeared earlier, right? This 5 was actually the length of AV1. And that's no coincidence. So in fact, in general, the singular values are equal to the lengths of our AVI. Okay, so the last thing we need to do is what's called the singular value decomposition. So this says we start out with an m by n matrix of rank R. So we can go back and remember that's the number of linearly independent columns. Well, then there exists a sort of almost diagonal matrix, but it just has some extra zeros. And these are not just 1 0. This can be, let's see, if D is R by R and that whole matrix sigma is M by N, the number of extra zeros in the column, number of extra columns of zeros is N by R, and the number of extra rows of zeros is M minus R. Okay. So essentially, remember before when we had a diagonal matrix, or diagonalizable matrix, that was P, D, P inverse. And now we're kind of, this sigma is taking the place of D, where we see our eigenvalues, except this time we'll see our singular values. And actually our V transpose is going to hold our eigen vectors, and U is going to hold our values AVI, sort of. So one thing we already know our eigenvector for lambda equals 25, for lambda equals 9. We subtract, remember it was 17, 8, 8, so we subtract 9 from that, and so we get 8, 8, 8, 8. We row reduce it, we get 1, 1, 0, 0. So a basis for the eigenspace of A transpose A at eigenvalue 9 is just 1, negative 1. And we want a unit vector in that direction. And that vector still has length square root of 2. So here is so we divide by root 2, and that's our eigenvector. So now our matrix V, we get by just placing our eigenvectors in here. So we had our first eigenvector corresponded to lambda equals 25. And our second eigenvector corresponded to lambda equals 9. And now our sigma is the matrix that we get by putting we want it to be the same size as A. Oh, and yeah, let me write this up here. So A is M by N, so sigma is M by N. And that means actually our U has to be M by M, and our V transpose has to be N by N. So our sigma, so in this case then, we're looking at A was a 3 by 2 matrix. So we put our singular values and make like a diagonal matrix, and then we fill out with zeros until it's the size of A. And then the last thing we have to put in is our U, which corresponds to our A times X. And so if you remember, we got our first A times X by doing, up here, we had this 5 root 2. Oh, except we have one more thing we have to do for our U. So our U columns, we call it UI, is 1 over sigma I times A VI. And we might also have to fill out some extra columns at the end. And technically we'd use Graham-Schmidt for that. We didn't do that section, so I'm just gonna fill that in for you. It's a straightforward computation that you can learn if you need it, but for now we won't include it in our work. So we have this first column corresponded to AV1 for our lambda equals 25. You do the same process that we did up here so we take our unit vector and we multiply it by A. So here is our unit vector for AV2. And I'm just going to go ahead and write down what we get. We get 1 over 3 root 2, negative 1 over 3 root 2, and 4 over 3 root 2. And then I'm not going to talk about how, so you can test that column. You can go back and try to compute that. I'm not going to show you today how we got the third column. If I were to ask you to do something like this on the test, I would fill in that third column for you and ask you what the first two columns need to be. And so this tells us that A equals, so first we have our U. So we have 1 over root 2, 1 over root 2, 0. 1 over 3 root 2, negative 1 over 3 root 2, 4 over 3 root 2, negative 2/3. Basically right now I'm just putting these things in. I guess we can be faster and put sigma as our second entry. And now we need V transpose as our last entry. So actually in this case, V transpose equals itself, but this is U, sigma, and V transpose. And with that, we will stop.